Hello everybody, welcome back. In this video, we're going to deal with our very first boss battle. Yes, so we're going to be solving this partial differential equation. So you're going to need to use all of the techniques that I've gone over in my previous videos in order to solve this one. So if you want to hone your skills, it would be a good idea to pause the video and to solve this one on your own before seeing the way that I go about it. So yeah, u here is a two-dimensional function, and it satisfies this gigantic first-order partial differential equation. So, alright, so notice that the first derivatives of u have constant coefficients, so the way to solve it is by using the coordinate method, or the change of variables. So these first two terms here can be written as the dot product of 1, 2, dot the vector with the partial derivatives of u. So, like that. So I'm going to draw this vector 1, 2 in the xy plane now. So this has a rise of 2 and a run of 1, so it's going to look like this. So this here is 2 and this here is 1. So the slope of this vector is going to be m equals 2 over 1. So the vector perpendicular to one of the vectors perpendicular to this is like this, and it has a run of 2 and a rise of negative 1. So the perpendicular slope is going to be the negative reciprocal of this, which is negative 1 over 2. So the vector would be run of 2 and a rise of negative 1, so like that. Now I'm going to dot each of these vectors into the position vector x. So, whoops, 1, 2, and then dot it into x and y. This is going to be x plus 2y, and this is going to be p. And 2, negative 1, dot it into the position vector, gives me 2x minus y equals q. So I'm going to make a change of variables to p and q from x and y. So my goal now is to use the chain rule to write these old derivatives in terms of the new variables p and q. So if I use the chain rule, dp dx plus du, second variable now times derivative of the second variable with respect to x. Alright, now the derivative of p with respect to x is just 1. That's just the coefficient of x here. So times 1. And now plus partial of u, partial of q. So the derivative of q with respect to x, that's just going to be 2. So that's the partial of u with respect to x. So now I'm going to find partial of u, partial of y. So it's the same formula as above, but now instead of x here and here, it's going to be a y. So alright, the derivative of p with respect to y is going to be the coefficient of y, so it's just 2. And now, plus partial of u partial of q times, and now the coefficient of y in here is going to be a negative 1. So, negative 1. Alright, now that we know our formulas for the first derivatives of u with respect to x and y, I'm going to plug them in now into the PDE up here. So, if I do that, the transform PDE is going to be this. Plus 2 and then plus 2 du dy. So du dy, the formula is going to be right here on the right side. So plus 2, 2, and then minus partial of u partial of q. And so now this third term on the left side here, 2x minus y, that's just going to be q. So I'm going to put plus qu equals. So now this right side, notice that if I multiply these two binomials, that gives me the right side. So let me show you. So if I have x plus 2y and I multiply it by 2x minus y, this evaluates to 2x squared and then minus xy plus 4xy and then minus 2y squared. So yeah, that gives me the right side. So on the right side, I'll have just PQ. Alright, so if I distribute the two, notice that partial of u partial of q cancels with this one here, and I'm just left with 5 partial of u with respect to p plus qu equals pq. So, as a result of making this change of variables to p and q, I have basically combined these two first derivatives into one. So I'm just left with this equation, this transformed partial differential equation here, which is much simpler. Now I can use an integrating factor to solve the transform PDE. So I'm going to start by making the coefficient of the first derivative 1. So I'm going to divide both sides by 5. Doing that gives me partial of u partial of p plus q over 5, u equals pq over 5. Now I'm going to use an integrating factor, I. So I equals e to the integral of the coefficient of u. So it's going to be q over 5 dp. Q is treated as a constant, so this evaluates to e to the pq over 5. This is my integrating factor, and now I'm going to multiply both sides of this transform PDE by I, and that gives me e to the pq over 5 partial of u partial of p plus q over 5 e to the pq over 5 times u equals pq over 5 e to the pq over 5. So the left side can be written as a derivative by the product rule. And the right side remains as it is. So now to get rid of this partial derivative with respect to p, I'm going to integrate both sides partially with respect to p. So on the left side, I have e to the pq over 5 times u equals, so now I have to integrate the right side here with respect to p, treating q as a constant. So I'm going to use Mathematica for that really quickly. Let's see what it says. So pq over 5, pq over 5 dp. Alright, so that's the answer. So to do this, we would just use integration by parts. I just want to avoid the algebra so that I can show you the real problem, or to focus on the real problem. So on the right side, I have pq minus 5 over q times e to the pq over 5, and now plus an arbitrary function of f of the remaining variable q, because I integrated partially with respect to p. So I have this arbitrary function here. So to solve for u, I divide both sides by e to the pq over 5. So on the left, I get u pq equals, so I'm going to divide these two terms here by q. So I get p minus 5 over q, and then plus e to the negative pq over 5 times the arbitrary function of q. Now that I know what u is, I'm going to change back to the original variables, x and y. So what was p again? P is x plus 2y, and q is 2x minus y. Alright. Alright, so I have x plus 2y for p, and then minus 5 over q, which is 2x minus y, plus e, negative x plus 2y, and then q, which is 2x minus y, all over 5, and now f, q, it's going to be 2x minus y. So this is our general solution to the PDE that we started with. So the final goal is to check that this is in fact the solution. So let me write this into Mathematica. Let's see, x plus 2y minus 5 over 2x minus y, x plus 2y, 2x minus y over 5, and then f, 2x minus y. Alright, what was the PDE again? Let's see. There it is. Alright, so the PDE is first derivative of u plus 2, first derivative of u plus 2x minus y, uxy equals 2x squared plus 3xy minus 2y squared. Is it correct? Yes! Yes! Huzzah! Alright, so we solved this PDE. So we used several techniques here to solve it. So we started by writing these two first derivatives as one by making the change of variables to p and q. Doing that resulted in a much simpler first order PDE that we could solve with an integrating factor. And then we finished it off by integrating both sides partially to remove the partial derivative operator on u. So we could solve for u, and then once we knew what u was, we could substitute back in the original variables x and y. So I hope this was helpful for you. I'll